So, let me say a few words regarding the context of this session devoted to eco-efficient transport and modern energy solution. And nowadays it is a banality to say that fossil fuels become scarcer and more expensive, and the threat of the climate change caused by the greenhouse gas emission increases. It is ever more important to consider alternatives in the fields of energy and transport. The STOA panel, Science and Technology Option Assessment, which is an integral part of the structure of the European Parliament, examined in July 2015 the opportunities that could be available for economic transport with a lower environmental impact, besides potential new energy solutions that could decrease Europe's dependence on oil and tackle climate change. New technologies could completely change urban transport system. Three basic strategies have been identified to foster the development and adoption of more efficient transport system. First strategy, the carbon use of transport must be reduced, cleaner fuels and propulsion technologies must be used, and transport flows must be optimized. Second strategy, there must be a shift among users toward more environmental friendly means of transport, as for example, the electric vehicle technologies related to the electrical vehicle technology, charging technologies, and fuel cells vehicles. The third strategy, the need to travel must be reduced through virtual accessibility in the workplace by using wireless and electronic communication. As you can guess, this strategy to be implemented requires a radical change of the mindset of the users. Eco-efficient transportation and economy of energy are directly related to renewable energy dealing with emerging production, sunlight and wind conversion, and energy storage with batteries and supercapacitors, for example. At the beginning of October, in the frame of Industrial Innovation Info Days meeting organized by the European Commission Directorate General for Research and Innovation, and before the STOA panel of the European Parliament, Professor Rodrigo Martins and Professor Elvira Fortunato have presented their vision regarding the emissions of the future and the role of materials in the field of energy, ICT, and health. A part of these issues previously mentioned will be addressed this morning by two outstanding speakers, Professor Sigurd Wagner from the University of Princeton and Professor Adelio Mendes from the University of Porto. Just a few words before leaving the floor to Professor Sigurd Wagner. For decades, Sigurd Wagner has been at the forefront of solar technology research, and he is considered at the present time as the father of the field of flexible and stretchable large area electronics. In 2009, he got the Sir Neville Mott Lecture Award at the occasion of the 23rd International Conference on Amorphous and Nanocrystalline Semiconductors. He is Fellow of the American Physical Society, Fellow of the Institute of Electronics Engineers, and corresponding member of the Austrian Academy of Science. Please, Professor Sigurd Wagner, for giving your lecture.
Thank you, Professor Tressot. I appreciate the opportunity to talk here. And I'm very interested in the themes that already have been covered. My own talk will actually cover facts that I think every one of you knows very well. I just give you my organization of these facts and my conclusions. The conclusions are very simple. We need substantially more really fundamental research to bring the world to fully renewable energy. The technology that exists now cannot do it. I'm talking about the challenges that we run into if we want to power Europe, the entire world with renewable energy. Here is my affiliation. If you are interested in this field, I recommend that you read the book by Professor McKay, Sustainable Energy Without the Hot Air. It's downloadable for free from his website. Professor McKay was a leading information theorist, but he took interest in renewable energy. And this book, or the file, is probably one of the best pieces of work covering the problem of renewable energy. I would like to just have a moment of silence. Professor McKay, at a very young age, passed away last year, and he's a really great loss to the energy community. So the main message that I have is we need fundamental discoveries, not technology, but discoveries to make the world running on a fully renewable energy supply. First, I'll cover this in two areas. First, how much renewable energy we can introduce now, and then just my own ideas on how we could overcome the limitations that come out of covering the point one. There are two principal sources of renewable energy today. That is wind. So here's a wind park, offshore wind park in Denmark. And then photovoltaics. Here's a photovoltaic field in Portugal. And when you look at the resources and think about the conversion to renewable energy, the first conclusion is that if we convert to renewable energy supplies instead of the supplies that we're having now, which are coal, oil, nuclear, petrol, that the renewable energy will be largely electrical, so we run into an electrical energy economy. And when you look at the numbers, then you will find that the production of electricity will have to go up by about a factor of 5 to convert from the current energy economy to a fully renewable energy economy that will be electrical. So there's a tremendous increase in electricity production from renewables, not a substitution alone of current electricity production, but a substitution of all energy use will require this factor of 5. In Europe has enough resources in principle to be fully powered by renewable energy. And I want to use two charts to make the point without doing the calculation. The wind resources in Europe are best, so the dark blue are the best wind resources, so there are some mountainous areas, but mostly close to the open ocean. What is missing from this chart, I couldn't find one, is that there are considerable resources offshore that are not shown here. And I think the offshore resources, in my guesses, are bigger than the onshore resources that are shown on the map here. The way renewable resources, sun and wind fluctuate. They vary from day and night, from summer to winter, and also they fluctuate depending on the weather. And to capture the production with some numbers that can be compared, they are typically measured in full load hours per year. So this is an average over the year. That is the installation, for instance, of a wind turbine. If the wind turbine were running at full power, how many the power that it produces over a year in actual conditions, how many hours would that correspond to in full power? So the year has about 9,000 hours, a little fewer, and you can see the wind resources here are 500, which means only 5% of the year you get full power, to 3,000, and the offshore resources are all at the lowest point on that color chart. They are 3,000 and more, so 3,000 hours of 9,000 hours is about a third of the time. Then the same chart exists for sun, except for some reason that I'll probably never learn. The good portions here are blue, and here the good portions, the bad portions are blue here. The right portions are in sun. And of course, as you realize, there's the hope that at some point in the future, North Africa will be able to contribute. And the best solar resources in Europe are available, would correspond to 1,500 hours a year out of about 9,000 hours. So what I just state here, and I don't show you any calculation, is when you look at the resources, Europe could be fully powered by renewable energy in principle. But when you look at the average availability of the important resources, then you will see that for wind, it's about 3,000 hours by 8,760, which is the number of hours in a year, so it's 35%. And for sun, it's about 20%. So these numbers, it turns out they're just from these maps, but when you look at actual performance of solar and wind installations, they fluctuate. Particularly wind has a much larger spread, and 35%, but the numbers are pretty close to what is actually available over a large region. So these are the conclusions from this discussion. Wind and sun would be able to fully power Europe, but the average annual availability is only 35% for wind or 20% for solar, which means if I had a wind installation that if it were running day and night all year long, it would produce 100%, but the installation doesn't get enough wind, so it produces only at about a third of its capability. So one basic economic problem with renewable resources, renewable generators, is that the capital investment you have to make is for full power output, but you don't get full power output. That's the main reason why the costs of renewable electricity generation basically is still too high. Even with subsidies, there's a problem. Large capital investment, but low power output, in contrast, for instance, to a nuclear power plant, which has huge, large capital investment, as we know today, but these plants run 90 or 95% of the time. So here is a chart that's from Golden, Colorado, where the US Renewable Energy Laboratory is located, of sunshine for the year of 2012. So here are all days of the year of 2012. What you have is on the ordinate, the magnitude of, say, of one of these points is the solar irradiance. Here's a scale for the solar irradiance. 1370 watts per square centimeter is the above atmosphere irradiance. At ground level, it's about 1,000 watts per square centimeter. And then each of these blobs is for one day. And you can see right away the three aspects of the variability of renewable resources. You can see that in January, top row, or in December, bottom row, there's little sunshine, but in the summer, in the middle, the sunshine goes up to high levels. You can see that of course, you can see that there's a difference between day and night. There's nothing at night here, and here it's black during the day. And you can see also the fluctuations that are brought in by weather. So for example, I picked out something in late November of that year, and you can see that when you have, even though you have fully installed power generation equipment, it is not made use of at that period because there's barely any sunshine available. So overall, you could produce enough, but it's not reliable. That's the basic problem. So there are some definitions. Actually, this field hasn't quite settled. I give you just some words, but they may change depending on who is talking about the field. From day to night and from winter to summer, that may be called variability. It is predictable, day to night, winter and summer. But variations from seconds to about weeks that are weather dependent sometimes are called intermittency, and they are not predictable or not predictable in the long term. You know when it's going to be day to night a year from now, but the weather predictions are not as reliable. So that's the category of intermittency. And just to get back to the term I already used, when you take all these contributions, more or less predictable, then you get over the year or some period the average availability. There's a very important point that is the two words on the lower right, that's called capacity credit. And the capacity credit is the reliability with which we can count on to solar or wind to supply power. And it turns out currently, because as I'll show you a little bit, the wind and solar power are backed up by conventional power generation. The capacity credit of these conversion techniques is relatively high. It goes between 0 and 1 or in percentage form. But if we relied only on wind, for example, the capacity credit is of the order of 0 because you cannot dispatch is the word in the United States. When a consumer wants electricity, you cannot rely on wind that it will be available. So you can get electricity, but it is not reliable at every instant. And that is captured by the term capacity credit. That also is a number. There are many studies about this, and as experience is acquired in current operation of wind and sun, these times are refined and better understood. Many of these are a matter of opinion as much as of fact, and the facts invade the opinion currently because there's so much operating experience. So sunshine here is variable and intermittent. We must find techniques to make solar energy reliable, and wind energy also. And the term that is used in standard electricity industry in the United States, it's dispatchable. That is, when there's a need, you can just turn up the generators and you produce more electricity. Now, the question is, when you look at capacity credit, how dependable wind and sunshine are. If you look at a chart that is not too different from what I just showed you, but it's from Germany from this January of the current year, then you'll see the following. So here the abscissa is basically the days in the month of January. It goes from December 31st of 2016 to January 31st in January, from left to right. And here is the power that was produced in Germany. The power, the whole German power production at the maximum. I see there's a problem from translation of my Macintosh to the PC. These things should not be here. The whole power production in Germany typically goes up to about 60 gigawatts, which is about twice the length of the scale here. I have 30 gigawatts marked here. And what you can see here is the production from wind and sun. It turns out all the shades of the bluish pastel color and these green pastel colors is all wind, and they're from different supply companies. So that's split up by the producers. And the little, this is January, the little yellow and reddish areas are sun. So they're not, in January, there's not so much sun in Germany. It's a poor country for photovoltaics. But the point to make is, here is a period of about 10 days in January where neither wind nor sun together produce more than about 10% of the electricity needs. So the capacity credit is very low. You cannot rely on these. So here is, a circled, and again, so at high penetration of wind and solar, if you had to rely fully on that as your power supply, you have a very small capacity credit. So even though enough renewable energy may be available on average, with these annual averages, for example, it needs to be fully backed up by conventional power. And I just want to illustrate that with the next slide. So wind, this is wind here, is also variable emittent. So both solar and wind must be backed up. And we need techniques that make wind and solar reliable. That's the key issue. These techniques don't exist. So here is all electricity in Germany. That's just, it's actually the same time period that I had before, but now it goes up to about 60 gigawatts. It's the total production. And what you have here is, the pastel green is all wind. The yellow is all solar. And the area underneath is nuclear power, coal, and natural gas. And you see how they fluctuate and how they back up wind and solar when they do not produce enough. So the current backup, wind and solar currently contribute substantially, but they cannot do it alone ever because they always need backup from the fully conventional power. And one of the big problems in the whole field is you put in capital equipment for wind conversion, wind turbines, for photovoltaics. These are expensive. And then you put in capital equipment for coal power plants and nuclear plants, and they're also expensive. So in a way, you demand that now the capital investment in power production goes up by a factor of 2 to make use of renewable energy. And that's not a long-term solution. There are many other problems associated with it, but the easiest way to explain it is in terms of money. You spend twice as much money for power plants. Not practical. So all the dispatchable electricity is generated by the means that we actually want to displace. This is nuclear and coal and gas. Now, the base load, this dispatchable has 2 parts, and the more reliable electricity that is produced day and night is called base load. So a nuclear power plant that hates to be turned up and down but wants to run steady is a typical base load supplier. But here's base load. There are 2 main suppliers of base load. That's coal. Here's a power station in the United Kingdom. And nuclear power, so this is the well-known plant in Flamanville in France. And these are the ones that sit in that gray regime of the preceding chart, and they provide all the backup for the conventional power. Now, there's a very interesting aspect that I want to show, an item that's very much discussed in the United States now, and that's called the California duck. And the California duck has the name because it kind of has the shape of a duck, the graph. This is from a wholesale organization for selling wholesale electricity in California. It's the principal, it's an organization of a number of power producers, and they run their sales as a single organization. And the power that you can, if you can read it, it goes up to 26,000 megawatts, so 26 gigawatt. That tells you, it's a large portion of California uses power up to about half of Germany, if we compare it with the scale. So that's the power again. And this is lowest March daytime net load. This is the lowest consumption in the month of March daytime it's actually 24 hours. And net load is what that compound of power producers sends out from their power producing plants. And it has a record for from 2011 to 2016. And of course, as always with these graphs, you never can tell the colors apart. But I just want to point out that these numbers that are bunched up on the abscissa, these are the hours of the day. So we go from 1 o'clock in the morning to 24 hours. And the colors are supposed to show the different years. You can't tell it. It's even hard to tell it on the original. The top curve is from 2011, and the bottom curves are the recent years. And what has happened is, so this is the people who send power from coal and nuclear and gas-fired power plants. They see in the old days, like 2011, that this is midnight, early morning hours during the day, and then it goes up in the evening. This is a typical California load profile. Because of increasing solar power, during midday, the electricity that's asked from the power companies has drastically decreased. So this is already an illustration that the power plants are available to produce maximum power, which they never do except exceptionally, even at regular, but now they are forced to produce less and less power during the day because solar power is available. It's mostly solar power, not wind in California. So this is one problem. They sit on something that costs money. They have to pay the banks for the interest rates on the construction costs of their power station, but they cannot sell power. It's even worse. Sometimes it turns out they have to sell electricity and pay somebody to take the electricity. That's the way it works, only a few times a year. But what is more serious is that at the end of the afternoon, when the power consumption rises drastically, all the power equipment that is now little used during the day has to be ramped up very fast. So if you look at the slopes actually have been going up since 2011. It's ever more steeper. If you look at that rate, I tried to estimate it, it corresponds to turning about 4 of these big power plants on per hour. So at 5 o'clock you run 10, and at 6 o'clock you need 14 to run. And these big power plants cannot be turned on rapidly. The only way to run, so nuclear doesn't want to be varied at all. If you have a nuclear power station, if you have a coal power station, you can vary, but it turns out the masses and the thermal gradients that are involved are so big you cannot ramp arbitrarily fast. These are huge rotating masses. So they're coping with this currently with all sorts of measures. One measure, of course, is that they try to organize power contributions and also selling power over ever greater regions in the West, just to level out the demands, because the demands in the various states are different from the demand here. So that's the California duck, and it is an illustration of the difficulty for conventional technology to handle these huge fluctuations. Now, here is an advert. I cut out an advertisement of General Electric Company. It's a gas turbine power plant. You can also turn generators not just with steam turbines from nuclear heat or coal, but you can run basically aircraft turbines and hook a generator up to them, and then you make electricity with gas turbines. And the reason why this is a plant outside of Milan, in the Piedmont, and I want to draw you to some faint writing, and therefore I explain it. They advertise, this is an advertisement how they refurbish this plant with General Electric gas turbines, and they say the load ramping capability, which says 50 megawatts per hour, no, per minute, I'm sorry. That is, they advertise how fast they can go at that incline of that black line that I have in the upper graph. That's becoming ever more important. That's why gas turbines are introduced more and more, because they can change much more rapidly than the old nuclear and coal. But they also, in this advertisement, they mention something else. And it says 65 megawatts per gas turbine minimum load level. That means all these power plants, including gas turbines, cannot be fully turned off. They have to run at a minimum level all the time, whether you need the electricity or not, because if you turn them off and have to start again, it takes hours to days to do it. That is, you cannot ramp fast. So to follow that very fast ramp, the conventional power backup has to run at a minimum level, regardless whether the electricity is used or not. And so that's why this California organization, at the minimum during the day, is paying other power companies in other states to take their electricity. They pay them to take their electricity because they have to keep their plants running for technical reasons. So conventional power is mostly coal and nuclear. Present growth in generation is from natural gas, particularly in the United States, because their gas is very inexpensive now. So all the power plants that are built now are natural gas power plants. So it's inexpensive, but one main driver is they can follow the fluctuations in renewable generation very fast. So here is a picture from my own home country. That's the hydroelectric project in Kaprun, which is a Celtic word. It means wild water originally. And it was built to collect meltwater and run hydroelectric power generations, because there's so much elevation difference. There are two dams for producing electrical power. But increasingly, they have become batteries for storing renewable energy. Because there are two successive lakes, as you can tell, what is done is these originally were built because they collect meltwater and then they act for load leveling during the rest of the year. In summer, for instance, when the climate is dry, you can do it. You cannot do that on a large scale for renewables. It's for a small country that it works. What is mostly used now is the water from this lake is pumped up during the night with the electricity that the power companies must produce but cannot use. And then it's run down during the day to produce electric power and send it off to elsewhere. And the reason why I actually took this picture is the blue one is what was built a long time ago for pumped hydro. But it turns out it's become so important that they built a separate line and a separate power station to double this capacity. So this is the most important way of storing electricity today, is to convert the electricity in potential energy of water and then back convert it. But and here is an example of the green area is when electricity gets pumped in, say, in Switzerland, for instance, from French nuclear power stations. That would be the green. And the red one, when the electricity is used and sent off during the day when it is needed. Now, there are other ways of storing not really electricity. This is not storing electricity, this is storing potential energy of water. But there are other ways, and here is a solar thermal power plant in Morocco. Nur Qazarat, and then the first semi-commercial power tower in Andalusia. These are basically, they look different, but they're using the same principle. In this field, there are tubes where fluid is heated by solar collectors, and then the heated fluid is used to make steam, and the steam drives turbines and then generate power. But here, the collection is not by fluid, the collection is by concentrating light onto a focal area where high temperature heat is used to heat basically a salt, and that heat is transferred to steam and then power generation. And the reason why I showed this is most, but not all of these plants have storage tanks. And in these storage tanks, the heated fluid can be kept for some time, and that serves for about 3 hours of power storage. So and then there are other storage techniques in development, so batteries, hydrogen bioelectrolysis, liquid biofuels. And batteries, if you look at batteries, say if Europe were fully running on electric cars, and you use the capacity of the batteries in the electric cars to, say, in terms of a power outage, draw electricity to some degree, not fully empty them out, you can calculate that you would get storage for about a few hours in the electric cars. So all the storage techniques that exist only last up to a day. That's the basic problem. So present and foreseeable storage techniques can compensate for variability and intermittency for about 1 day. And so we need something more reliable that can go from season to season even. And so the conclusions that we have, this is my part one, is we will have an all-electric economy in the long run. We could power all from wind and sun, but they are not reliable, and the storage techniques perhaps could hold out for a day, but not longer. That is, they're not adequate, even foreseeable storage techniques. And therefore, I speculate, right? So this is the speculation portion. Every one of you, many eminent scientists here, you can go and speculate also. So my background is in solid-state electronics with materials, and one of the most, these are all existing ideas. These are not new ideas, but I just rank order them in my favor. If we could transmit electricity from the day to the night side of the Earth, or from north to south, then there's no problem if we had easy transmission. If we could directly generate solar fuel, then we have a storage medium that we can use when fuels are needed. So you could use it for a power station that doesn't address the fluctuation problem. But for instance, you could use solar fuels to power airplanes. For example, they're likely to, for a long time, to run on fuel. And then is my own specialty. I smuggle in here the harvesting of hot electrons. And I will focus on on superconductivity because I think this is the most important. So my colleague Jim Sturm, who is a star teacher, he always teaches the student to think like an electron. And the way we make students think like an electron, I have a standard scale. The energy is up, and some distance is on the abscissa. That's the basic scheme in thinking. So you have an electron at low energy, something like wind generators or solar panels or nuclear power station or whatever, they raise the electron energy. So this is the basic process. And then you can do several things with the electron. One is you can transmit it over a long distance. Right? This is what we have it, we live with it, but I want to have an even longer distance. The energized electron is also a chemical reactant. So you can make fuels. If you provide energy to electron, you can use it as a reactant. And this is a little tricky, and so I'll go fast on this. Solar panels could double their power if there were techniques to harvest the energy of electrons within picoseconds. That's currently not possible. The harvesting is done between nanoseconds and perhaps milliseconds, but not within picoseconds. If you could, within picoseconds, you could double the efficiency. And then solar electricity would be so cheap, you just hydrolyze water and you have hydrogen. So this concept of transporting electricity around the world has been around for a long time. The person who captured this was Dr. Cubano, who was first research director and then later on the chief executive officer of Sanyo Electric. And he said, we need superconductivity. Now, superconductivity exists, but not under conditions where it's practical to use. So that's his idea. Now, if you transport electricity over a long distance, this is done today to an increasing degree. So here we have now, instead of energy, I write voltage, it comes out to the same thing, and distance in kilometers, a little more specific than before. And we think in terms of 1 million volts and 20,000 kilometers, half around the Earth. Right? So summer to winter, day to night needs 20,000 kilometers. The longest, so the currently most efficient way of transporting electricity is ultra-high voltage DC transmission. Very technical, but it turns out that it has the lowest losses, DC transmission. Actually, we are here in Lisbon. One of the first lines that was built, but not really used in that way, was in Cabora Bassa in Mozambique, a long time ago. This is becoming, it's very expensive, but it is becoming more and more important, and not surprisingly, China is the leader. They have the longest lines. So in these cases, over 3,000 kilometers, that's currently the longest lines, you lose 10% of the voltage. So you go in with 1 million volts, and because there's resistance, there is what's called voltage drop resistive losses, and out at the other end come 90% of the power. That means if you use this type of technology and ran 20,000 kilometers, you would lose 50%, which is inadmissible. It is not a realistic technology if you use half of the power that you want to get by transmission. But if you had superconductors, you might lose much less. So ideally, like we have heard before, scientists overpromise. They say it's loss-free, but it's clear that if you had superconductors, they would lose much less. So now, superconductors exist, but there's a problem with them that needs to be resolved. So anyways, you see if we could transmit current from day and night, everything would get fixed. And so the other two items that I want to cover, I'll do it briefly, they are much less important than this. The problem with superconductivity is it's cryogenic. That is, currently you need liquid nitrogen or liquid helium, and it's impractical to run 20,000 kilometers in a jacket of liquid helium. So that's out of the question. And what is needed is, by the language of superconductor, is called high temperature superconductor, but our daily experience, that is room temperature. What high temperature superconductors means that for somebody who's used to work with liquid helium, it's high temperature, but actually we want room temperature, something that superconducts up to about 100 degrees C. Now, if you look at superconductors, there are many. And I use a chart that is biased by the use of superconductors, which is in magnets, in high-performance magnets. And so the graph here has magnetic field strength, which is how capable the superconductor is to support the high magnetic field, which is not important for us. But the temperature scale in Kelvin, so it starts here, is the important one, and it shows that there are to the right of each intersection with the abscissa, it doesn't superconduct the material, but to the left, it does superconduct. So it behaves like a normal conductor to the right, which we don't need, but to the left, it has this wonderful property of being loss-free. And the reason for showing the graph is that superconductors started simple. Camerlingons discovered it on Mercury, so it's just an element. But it turns out there are all sorts of compounds for material scientists. They are basically unrelated, except the most recent one had oxygen in copper. But then there are things that are pulled out of a hat. Nobody knows really why. So there are many different materials that are superconductors. And the basic notion is research for superconductors, like many other areas, has been full of surprises. People discover superconductivity where they don't expect it. There are very different classes of materials that can be superconducting, and there's no guiding principle. And so you know what this means, right? It means just exploration and search. There is It is a highly desirable goal. There's no guiding principle. There is no theory, even if you believe the theory, then that says there's a physical limit to the superconductivity. Nobody knows. But it is very important if we could overcome it. And actually, in one of the articles on superconductivity, a review article, I found this sketch, I think it's by a family member of the author of the article, that relates to Monty Python. There's a series of skits in Monty Python where the Spanish Inquisition appears by surprise. And the sketch says, well, this is how superconductivity developed. I think the leftmost person is supposed to be Camille Lingons, and he discovered it in mercury. So metals can be superconducting. Then the next one discovers it's in alloys also. Then somebody discovers, oh, even organics can be superconducting. And so this is an illustration of the fact that nobody knows where to look and how to find it. But there's also no physical principle that tells that it can't be found. So we need a predictive theory of superconductivity. All the theories so far have been explanatory, but not really predictive, as it turns out, and a sustained exploration of materials. That's perhaps the wind and solar are on their way. This is perhaps, in my opinion, the most important research area for renewable energy, even though it's hard to convey. Now, perhaps I go faster because I made my point. I have two other examples. If you do solar photoelectrochemistry, we have our think like electron scale again. Up is high electron. When you have a photocatalytic electrode, then a photon from the sun will put up the electron to a high energy. What you can do then, if you have 4 electrons and they go onto water, you develop hydrogen. And then the electron, which is conserved in this, comes up in the form of OH- ions. Then what happens is these electrons can return to the solid material where they were coming from and were excited. So this is a cycling the electron. The OH-, I couldn't write it in any other way, it gives up 4 electrons back to the material, and it makes O2+, and we have split water into hydrogen and oxygen. So this is an example for making hydrogen of water, and it's an example for using the electron as a chemical reactant. It's a very active area of research. The main problem is that we need a material that hasn't been invented yet. It has to absorb sunlight strongly. It has to have a catalytic surface, and it doesn't corrode. There's no material that meets these conditions, and again, nobody knows whether there can be one or should not be one. It's not clear. Let me go and skip this, because we are late in time anyways. This is my own specialty babies, the solar cells. Preliminary conclusions are we need discoveries, not so much inventions, but discoveries. In superconductivity, in photoelectrochemistry and associated areas, for instance, artificial photosynthesis, and also in hot carrier capture, where you can take the energy of electrons out in picoseconds instead of a longer time. That would reduce the cost of solar electricity, and that would help us to go to a fully energy sustainable society. I want to just add there's a context. This was just science and technology. And here's a very personal story, but I have felt and seen it. In 1974, so I'm a co-inventor of the copper indium selenide solar cell. That was in 1974 at Bell Labs. At that time, there was a big enthusiasm in renewable energy, not for environment, but for energy security. And in 1978, here I show President Jimmy Carter how a solar cell works. So the president came and was interested in how this stuff works, right? Well, it took about another 30 years before the solar cell really began to be commercialized. So how did this happen? This was essentially, in my opinion, strictly a consequence of politics of the time. Carter was of one party that was renewable energy friendly. His successor was not renewable energy friendly. Essentially, there was almost a battle against renewable energy for a while, and that delayed the field by 10 or 20 or 30 years. So politics, as we have heard this morning, or talking to the public, explaining it, is extremely important. And then there's another aspect. This is my last slide. There are 4 solar cells that are commercial. Now, so when you see these fields, so when I look at them, I can tell them, but they're always, from far, they all look pretty much the same. 4 technologies, and the technologies are captured by the chemical composition of the material. So silicon dominates. It's 90% or even more. Cadmium telluride is the leading thin film solar cell, and then there's amorphous silicon and the cell that I mentioned already. These solar cells were all invented at huge industrial labs at their best times. Some of them don't exist anymore, like RCA labs, and others are not really fundamental research labs anymore. And they were discovered 60 to 40 years ago. This is the technology that's out there. It's very important, that should be improved. And so I leave you with 2 questions. One question nobody really knows how to explain. Why were these invented? So they were part discovery, part invention at big industrial labs in their best days. When you look back at the history of these labs, they have all faded in some degree. That was their best days. The best days meant they trusted their researcher. They hire only people whom they think they can think on their own. And when you wanted to do something, you explain it to your boss, and the boss says, okay, go ahead. And that was the research proposal that you had to do. And also, why did it take 30 or 40 years to reach the market? So the answer to the first question has to do with how to organize research. And everybody will have an opinion about this, but it must be, these were huge interdisciplinary organizations. So at Bell Labs, there were about 800 PhDs in the fundamental research division. The whole lab had 20,000 people, and the fundamental research ranged from astrophysics to semiconductor physics and economics and social science. And they were talking to each other at the lunch table. But the 30 to 40 years, so this is a question of managing discovery and invention. The second one is a question that relates to society at large and to politics. So I want to leave you with these 2 questions, and thank you very much for your attention.
Thank you very much, Professor Wagner, for this interesting talk. We have time for a couple of questions. Yes.
Thank you very much for this very insightful presentation, and also for making the point that we need breakthroughs in science and a long-term vision. Talking about breakthroughs in science, research on geothermal is really on the move, with a lot of breakthroughs being made. And I realize you focus primarily on electricity, but for heating, geothermal appears to be a pretty robust and constant add-on, supplementing other sources of sustainable energy. It's part of the Green Deal in the Netherlands, and it's taking off quite quickly in a number of countries in Europe, but also in Mexico and in Indonesia. Could you comment on that? Could this be part of your long-term vision? Because things are changing.
Yes, so I agree with this, and geothermal means 2 things, as you know. One is to use the heat of the earth, and the other one is to use the earth as a storage medium. And the latter is already spreading because it adds tremendous value to electricity in heat pumps, right? So that is a matter of course. The geothermal resources that can be used, that are hot enough to can be used to produce electricity, are a little more difficult to access than the geothermal storage, which takes you 100 meters down, right? So this is a very good point. It is clear that geothermal storage in connection with heat pumps is indispensable for the future. This is clear because it is such a high added value to electricity. You know, the coefficient of performance of heat pumps is so good that it beats even just burning coal and using the heat. No? The geothermal resources are relatively easy to come by locally, but in many places they're very expensive to exploit. And so I think that will take time.
At this moment, there are many developments going on in the drilling technology, drilling in magmas like Iceland, but also drilling in relatively cold countries like the Netherlands to, let's say, 4 kilometers to extract heat, which is, of course, a major
energy
issue
consumer.
in terms of the total energy budget. So I think it's very important to differentiate here the use for electricity and for heating. Yep. And coming back to your point of the need for constant supply, I would be very curious also about your views about how to figure this in the future equations.
Well, I think unless there are methods for leveling out energy beyond a day, it means that either we stay with 30 or 40% renewables forever, or we invent something. I think there's no, currently the economies cannot be made fully, even though the renewable technologies have proven themselves. For instance, you mentioned geothermal, but certainly solar and wind are full-blown technologies now, and their costs are coming down. But they just won't get above 30 or 40% under these conditions. And they will be also very expensive, because you need to run 2 power plants that complement each other. We need, I think this is a call for science. I am biased towards material science. There are many other ways of looking at it. But I think, for instance, if you had a high temperature superconductor that you can string like power lines now, it would be totally revolutionary and would allow you to go almost 100% renewable. That's just the point. It's a speculation, right? But it's believable speculation.
Another short question.
Is it possible to beam energy up to a satellite and then back down as a way of transmission?
Yes, it's possible, but it costs. Yes. I mean, the idea has been around for a while. Tests have been made, you can do it, but when you look at how much you have to ask the bank for, then people don't want to do it. So when it came to pilot demonstrations, nobody wanted to pay for them. So this is a very good point. Yeah? Excuse me? Yes. It's the same problem, right? When you go from satellite down, the satellite, this is a serious piece of equipment, not just satellites that we are knowing now, but also you have to collect it over a very large field, and immediately what happens is, the question is, what happens if the satellite gets out of orientation? Will you fry my city? So this, you know, the US is basically officially a paranoid country. Unofficially it isn't. But there's always this threat, right? And immediately the question will be, will the Chinese reorient the satellites? You know? so this is in a mix that goes beyond science, and you know, everybody can have an opinion on this. No?
Thank you very much again, Professor. Mr.
Yeah.
Wagner.